You're going to be a sin. I'm just kidding. Actually, yeah. I'll do it.
All right. How's everyone doing today?
Wonderful.
That's good. Pretty good. All right. So today we are going to be doing our third lab, and we're going to be doing a 2D unbraced frame. So moving up. So we're going to consider the 2D braced frame shown in figure 1. The model consists of 3 bays that are each spaced at 10 feet and 3 stories that are all spaced at 12 feet high each. And we're going to consider the self-weight of the structure this time. We're going to be using kips and feet. Going to be using steel. The section we're going to assign to everything today is going to be a custom plate girder. The dimensions I'll give in figure 3 here, and the loading is shown in figure 1 here. So here is the structure we're going to be analyzing today. 3 bays wide, 3 stories tall. Dimensions as given, loads as given here. So some uniform, some triangular, some point loads. We've done all of those before. And here are the dimensions of a plate girder we're going to be telling SAP how to build and run for us today. A lot of the time, well, most of the time, when we have sections that we want to put into SAP, it'll be from a standard catalog, and we can pull it from a database that's already there, like from the AASC database. However, sometimes when we need to go and build up a custom section from pieces of plate steel, we would need to tell SAP the dimensions of that so that it can go and calculate the correct cross-sectional properties for this shape to go and do the analysis with it. There's a couple situations where we might need to go and create a custom built up section like this if we're doing some really custom situation, or if we need like really, really deep beams that are way deeper than like the standard beams go. Like big plate girders on bridges come to mind. Sometimes those can be, 10, 15, 20 feet deep, very large. And, regular rolled sections only go up to 44 inches deep. So that's an option if we really need a deep beam here, or sometimes if you have like a transfer girder where you need to like move a column over to another space on a lower floor, you'll go and put like a really thick beam underneath it so it can move all that shear and moment loads over. And oftentimes plate girders are useful for that application because we need to be able to size them appropriately for the tasks. So any questions on the frame here? We're going to be showing you how to make your own sections and showing you how to do frames. All good? Cool. So let's get SAP up and running. And yeah, we'll get started on the lab then. Is everyone able to finish their other lab and get that turned in and everything worked out for that? Okay. All right, so let's get started by making ourselves a new model. It'll take its time to get all the gears rolling there. Okay, and now when we have the new model window here, first thing we want to do is set our units. So the units we want to be using today are kips and feet. So we'll go in the drop down, select kips and feet. And then the template we want to be using today is going to be the 2D frames template. So that's should be at the far right of your top row there. So we'll go and click on the 2D frames template there. And we see we've got a decent number of options here. So first option is the type of portal frame, or the type of frame we want to generate here. Now there's a couple options. There's a portal frame, and that's the one we're going to be using today. And there's a couple braced options, and we'll talk more about those next week. So a portal frame is kind of just those regular rectangular bays like that. There's moment connections at all of the corners there, so all the lateral loads that get applied to the frame here get transferred down the columns through those moment connections. In a braced frame, we'll have these kind of diagonal bracing members in some of the bays there, and those will help use axial capacity of those to transfer the loads down to the foundation eventually. There's reasons to use some and reasons to use others. We'll get more into that in the next lab. But for today, we're going to be using a portal frame. It's a real nice typical frame, easy to use and design. So we'll keep that on portal. And then over here, lucky us, in our description for our problem, we have regularly spaced bays and regularly spaced stories. So we can go and use these boxes up here, and we don't need to define a custom grid spacing. Unfortunately, usually in a lot of buildings, we do not have uniformly spaced bays or story heights. So usually you need to go and make one. But for today, we're keeping it simple. We'll just use boxes up top. So we want to put in 3 stories and 3 bays. The story height, let's see here. That's going to stay at 12 there. And our bay width, instead of 24, we're going to set that to 10. Now that's pretty skinny for a steel structure usually. Usually they're wider than that. You don't need that many columns, but it's the lab example we're doing today. Okay, next thing we can do is we can create our section down here. So this is where, like last week, we can go and import a section and assign it to our beams and assign it to our columns. But we can also go and, instead of importing one, we can go and create one. So that's what we're going to do today. So we'll click on one of those plus buttons to get to the frame properties here, and we'll click Add New Property. Now, what type of shape do we want to define? We're defining a plate girder. It's going to be eye-shaped, so we're going to go and click on the eye/wide flange button here. And now we have this menu here. You might recognize this. This was one of those menus that pops up when you import a shape, right? Except this time, instead of having all these options grayed out here, we can go and edit them because we're going and creating our own shape. So first thing up top here, we have the section name. And we can go and call this whatever we want. For purposes today, I'm just going to call it plate girder. If you've got a big project and you've got a whole bunch of these, you can create whatever plate girder designations you want, or whatever type of designation you want for each of them. But that's what the section name is going to be called. And then down here, we have a bunch of measurements. And these go and define the different dimensions of our eye shape here. So first off, we've got T3, which is the total height of our shape here. We've got T2, which is the width of the width of the flange here. Then we've got TF, which is the thickness of the flange. And then we've got TW, which is the thickness of the web here. So first off, T3 here, that is going to be 10 inches. So what we're going to do is we're going to put in 10. But before we get too far, let's think what our unit's going to be. If we look in the bottom right here, we see that our units are kips and feet in Fahrenheit, just like we set them. But if we put in 10 here, that's going to give us a 10-foot tall beam. Useful for very large bridges and structures like that. Less useful for the building we want to be modeling today. So what we want to do is have it be in inches. So you can either type in whatever 10 inches is in feet, so 5/6, or you could put in 10 there and then use the double quotation there for inches. And then if we go to another box, that'll go and convert it to what it is in feet. So we see we put in 10 inches and that gave us 0.833 repeating. And that's, 5/6 of a foot, which is 10 inches. So we'll do that again for the top flange width, T2. So that's going to be 4 inches. So we'll put in 4 inches there. Then we'll have the top flange thickness, which is 0.35 inches. And then we'll have the web thickness, which is 0.3 inches. So far we've got 0.83, 0.33, 0.029, 0.025. And then we've got 2 more boxes down here. And these are the bottom flange width and the bottom flange thickness. Now, in our section, we're doing it so that it's doubly symmetric. So the top flange is the same as the bottom flange. In some situations, like if you're making a composite beam so that you have the steel on the bottom and it's composite with like a concrete deck on top or something, that's a pretty popular use of composite beams. An efficient way to do that is to have a large bottom flange and a really small top flange because the concrete's doing most of your top flange duties there. And you'd want more steel on the bottom. So that would be how you'd model a beam that had a bigger or smaller bottom flange than the top flange. But in this case, we want them both to be the same. So we're going to use the same numbers we used for the top flange here. So the bottom flange width is going to be 4 inches. And the bottom flange thickness is going to be 0.35 inches. So just like the top flange up here. Make sense? So the numbers you get should look the same as the ones I've got here. 0.83, 0.33, 0.02916, 0.025, 0.33, 0.02916. Okay, then down here, we've got some other things we can do. This is where we'd go and change the material. So a lot of the times if you're building up a section, you'll have a whole lot of different options for the types of plates that you can do. So there's a whole lot of different grades of plate steel you can use. Doesn't necessarily have to be a 992 FY50. This is where you could go and define a new material. We're not going to do that. We're just going to use this material that is default here. But this is where you'd go if you did need to model a yield, a steel or something with like, a higher yield point or something like that. So once we have all these options in, we'll press OK. And now we've got our new section, plate girder. And then we'll press OK. And now plate girder has been populated to beams here and columns here. Now, usually we're going to be using different sections for beams and columns. For simplicity today, we're just going to use this one for both of them. Any questions on that? Okay. And now one last thing before we press OK. If you notice in the picture here and kind of look at it closely, the boundary conditions it has modeled are little triangles there. So those are pin supports. And that's usually a pretty good conservative assumption for a column to foundation connection there. However, in some situations, you can also say those are fixed supports depending on how you detail that connection and how much moment it can transfer and stuff. If you look at the model that we want to be making today, we want these to be fixed supports. So by default, this gives us pin supports if we keep reactions on. Now, I usually uncheck this so that I remember to actually go and put in fixed supports, or I'll forget and they'll stay pinned and it'll give us different numbers. So I'll uncheck that and then we're ready to go. So I'll press OK and it will go and generate our portal frame for us. Let me close that. And now we've got our frame. Any questions on this? Okay, cool. So first things first, let's go and assign all of our fixed conditions at the bottom there. So we'll go to Assign, Joint, Restraints. We'll click on Fixed here, then press OK. And once you've done that, you should see we've got some rectangles down at our foundation here, and that is the symbol for a fixed condition in SAP2000 here. Any questions on that?
Was it restraints or constraints?
Restraints. Yeah. Constraints are different. We don't need to get into that. That's advanced stuff. We don't really need useful stuff, but out of scope for what we're trying to teach today. So now that we've got these on, that will bring us to all of the geometry we need to model for today. And now we can start on our loads. So the templates are really nice because they get you pretty much all the way there with the geometry. If you've got a pretty typical structure you need to model there. If you got something less typical, I usually just go and draw it in AutoCAD, then like import it in here. And I'll show you how to do that in, I think, one of the later labs. Okay, so we've got our structure here, and it's time to do loads. Now, before we do that, there's one option I want you guys to change in your model here, because in version 22 of the program here, which I found out after we went and upgraded and all that stuff last year, there's a couple slight bugs that happened when they were creating this new kind of graphics engine that goes and drives all the pictures you're seeing here. When we draw a uniform load in a 2D frame like this, it goes and crashes the program. I don't know why. It works fine in 3D. It works fine like on the 1D beams like we did last week, but when we do it in 2D, it breaks. They know it's a problem. They fixed it in the next version of SAP. But in the meantime, what we need to do is we need to go to Options here, and go to Graphics Mode, and then you should see a blue icon here that's called Classical Plus. We want to click on that. And that will go and switch us back to the old graphics mode. It used to work in that. They went and added a new one that supported the DirectX drivers. And that's where I guess a couple bugs worked their way into the program there. So any questions on that? Options, graphics mode, and then we want to click Classical Plus here. So hopefully that's not going to be an issue too much longer, but just something I had to find out last year after I spent 20 minutes crashing my program on loop because I couldn't figure out what was going wrong. Okay, so we've done that. Now we can add all of our loads. So what loads do we want to add? So we're going to have 5 kip per foot uniform loads on our outer bays. And then we'll have triangular loads that have a peak of 10 kips per foot on the inner bays. So let's start with our uniform loads. So let's select our outer bays here. We'll go to Assign, Frame Loads, Distributed. All of this is fine for now. In uniform loads, let's just put 5. Press OK. And now we've got our 5 kip per foot uniform loads on our outer base here. Now we'll do the same thing for our center bay. So we'll go to assign, frame loads, distributed. First things first, let's set our uniform load back to 0, because if we don't, it's going to add an extra 5 kips per foot there, and that's too much load, and we don't want that. So we'll set that back to 0. And now to go and create a triangular load like that, we'll go and use the trapezoidal loads function down here. So at a relative distance of 0 along the beam, we're going to start out with no load intensity. So right here at the start of the triangle, if there's no load. Halfway along the triangle, so that's going to be 0.5. We're going to have 10 kips per foot intensity. So that's halfway along here. And then it goes and tapers back down to 0 all the way at the end of the triangle. So we'll set that to 1 and have 0 there. And then for the last box, we'll just set 0 and 0. So I've got 0, 1/2, 1, and 0, and then 0, 10, 0, 0 in the first and second rows, respectively. Any questions on that? Make sense? Perfect. So we'll press OK there. And now we've got our triangular loads. All right. So now that we've done our uniformly distributed loads and our triangular loads, let's go and add our point loads. So we've got a 20 kip per foot, or sorry, a 20 kip point load here. So we'll select that node. We'll go to assign, point loads, forces. In the force global X direction, we'll put in 20 in force global X here because we have the load going in the positive X direction. Press OK there. And then we will do that for the next 2 loads, or the next 2 stories. So we'll select the next one, go to assign, joint loads, forces, change the 20 to a 40, press OK, and then do the same thing here. This one will be 60, and then we'll press OK. Yes. Let's see. Okay. So it looks like you might accidentally have that one selected too while you were applying it. Yes. So let's select that frame again. Yeah, just click on it again. And then go to assign. Frame loads. Okay. Yeah. And we're going to set that back to 0. No, I think that's yep, set that to 0. And then press. Oh, I'm sorry. Set that to 1 and then set all those to 0.
Do?
Okay, so that should be all the point loads then. So add your point loads 20, 40, and 60 on this side of our structure here, 1 for each floor. And once we've done that, we've modeled all of the loads we need. So we finished the geometry, we finished the loads. We don't need to change our self-weight because we want to consider that for the structure this time. So now we're ready to analyze. So we'll go and press play here, or press the run analysis button here. And we're going to turn off the model analysis, click run now, and it'll ask us to save it. So let's make ourselves a new folder. Then we'll save it there, and then it will run. It'll take a second, and then when it's run, it'll show you the deformed shape, and it should look something like it's getting pushed over a little bit. Everyone able to run their program and get something looking kind of like this? Anyone get anything different? All right, cool. So now that we've done this, let's look at the deliverables. So for the deliverables that we want to find for our report, let's look at, first, we want to find the reactions. So to do that, we'll go to display, show forces, stresses, joints. These are all good, so let's press OK, and we'll get our reactions down here. So we've got our horizontal and vertical reactions. If you notice here, these are all counteracting those horizontal loads, which is good. But there's enough horizontal load that it's actually managed to reverse this first column here from being in compression to being in tension. So we need to be careful with, large loads like this sometimes, that we see the whole range of forces that our elements can be in. So we know how to detail all of our connections correctly to handle all that. So we've got the two force reactions here. And if you remember, these are moment reactions. So if you want to find the value of your moment reaction there, what we can do is we can look at this in a 3D view here. And the moment is drawn in the third direction there. So that's because the moment, it's shown with this double-headed arrow here. The way they draw that is it's drawn about the axis it rotates about. And we use the kind of positive curling right-hand rule here to show the positive direction of that one. And that will go and show you those. So in the 2D frame there, the moment's about the y-axis, so it plots the arrow along the y-axis there. I don't need to see these in your screenshot, so if you just want to show me this view in the screenshot, that's perfectly fine. If these values are right, the moments will be right. So no need to worry about, angling a 3D view to get all the numbers in there. Okay, any questions on that? Yeah. How to get to or get out of? Press the XZ view button here. Okay, so we've got that. Let's see what our next deliverable is. It's going to be the deformed shape. So to get to the deformed shape, we can either go to display up here. I showed you guys about these buttons here, right? Okay, cool. Yeah, so we'll go to the deformed shape button. That's also here. I'll turn on wire shadow. The rest of these are good. So we'll press OK. And we've got our blue deformed shape in the foreground, our wire shadow in the background showing the undeformed shape. This is exaggerated. Actually, in this case, not that much. But this will be the deformed shape of our structure here. So that'll be good for our report there. Next thing we want are the story drift values. So these are the horizontal displacements at each of the stories. So if we look at the horizontal displacement for each of the nodes on a story, so horizontal displacement, that's going to be U1. So right here, we've got 0.3946, 0.395, 0.3955, 0.3962. You notice all these values are really close to each other. So what happens when we have a structure with a framed structure like this, and we have lateral loads applied to it? Because these floors are very stiff axially like this, compared to the open space between the floors, they effectively move as a rigid body. So not quite, but almost close enough to say it's pretty much moving as a rigid body. So because they do that, what we can do then is say we can give basically the whole floor a single displacement value, and it's going to be about that much displacement. It'll vary a little bit between parts of the floor, but it's close enough. It's a good engineering simplification there. So when we do that, we can call any point on this floor here, and it'll give us our story displacement value. And we want one of those for each floors to see how much each of our floors is going to move, basically. That makes sense? Usually I go and pick them on the right-hand side here, but any of them should be fine. And for when we're grading the lab reports, I make sure to pick the whole range. So it doesn't matter which one you pick, but I usually prefer to take them on the left-hand side here. That's just my preference, though. Or right-hand, geez. Okay, any questions on that? Okay, so for our story displacement values here, for our first floor, U1 is 0.39 feet. Second floor is 0.85 feet. And our third floor, it's going to be 1.14 feet. It's our story drift values there. And if you notice, 1.14 feet, that's like 14 inches or something. That's a lot for a 3-story building to be displacing. So this is probably a little under-designed for the loads we have being applied to it right now. Okay. So that is our third deliverable there. Let's see here. The fourth one here, the shear diagrams with values of the max shear in the second story beams. Okay, so let's go and look at our shear diagram. So go up to frames, cables, and tendons up here. And our shear diagram will be shear 2-2. And we'll click on show values down here. And then we'll press OK. And we get all of our shear diagrams for each of the frame elements in our frame here. So we see on all of the columns, we have nice uniform shear diagrams here because there's nothing being applied in them. And then on these outer bays here, we have nice linear diagrams because we have those uniform distributed loads. And then in the middle bays here, we actually have these kind of quadratic diagrams that have an inflection point in the middle due to those linear triangular loads in there. So if you think about how the shear diagrams should work from those distributed loads, you can justify to yourself why these should be the diagrams here. Okay, so we've got our shear diagrams here. We've got all the numbers there. One trick that helps when you're trying to plot these and look at all the numbers that might be on top of each other is using the object shrink toggle up here. So if we click that, that goes and shrinks all the diagrams, and that makes it a little easier to display them if we're trying to take a report or something like that. Yeah, so that's a nice way to clean everything up a little bit. So we'll have this for the report, and we also want to find the maximum value of shear in our second story beams. So to do that, let's look at our second story beams. That's our first floor. Here's our second floor. So it will go and write out the maximum value of shear in our diagrams here that we'd want to look at. So we can just look at these numbers and see which is biggest. So we've got 57.98, 53.5, and then 57.04. So looks like 57.98 is our biggest one here. What we can also do is we can right click on the beam and it will bring up this menu here. And this has more information on what we're going to see there. So this has our loading. It'll have our shear diagram, our moment diagram, and then an approximation of the deflections here. So if we want to, double check our maximum values in here, we can look at these diagrams as well. Make sense? So we'll have our picture of all of our diagrams here, and then we'll also go and say what our maximum shear is in our second story beams here. Now, why would we want to figure out what the maximum shear in all of these beams here is? Well, generally, when we're building structures, while we do want to try and optimize things as much as possible so that we're using the most efficient section, we also don't want to make it so that every single one of these shapes is going to be a different section, because that's just going to be a nightmare trying to cut up all the different beams and put them together in the shop. And then it's going to be a nightmare for the people actually trying to build it because they're trying to figure out what beam goes where. So generally what we try and do is we try and keep them about as similar as possible as much as we can. So what we'll do here is figure out what our maximum shear is and then size all the beams on this floor to be big enough for that to, keep it efficient, but also not make every single piece different and just a nightmare to work with. Make sense? Okay, cool. And our last deliverable is going to be our moment diagram. So it's going to be just the same we did for shear. So we'll go up to here, frames, cables, tendons. We'll click on moment 3.3. Then we'll press OK. And we've got our moment diagrams here. If we look at it with and without object shrink toggle, it does help a bit. So those are our moment diagrams. And we also want to find the maximum moment in our second story beams too. A little harder to tell right off the bat here. So let's right click on them to see. We see here we have a maximum moment of minus 191.87 kip feet. So this will give you the max value here. In this one, our max value is minus 192. And then in this one, our max value is minus 211.2167 kip feet here. So this one's the largest, so that's the max moment that we'd want to design those beams for. Now, you'll see that we have both positive and negative moments on here. And what I mean by max is maximum magnitude. I don't care if there's a positive or a negative sign in front of it. When we're designing steel, that sign doesn't really matter too much. It just tells you where the tension and compression forces are going to be on your beam there. And like when we're designing with concrete and timber and stuff, that'll change how we detail the connections and like where to put all the rebar and stuff in your beam. But when we're just trying to size the size of our beam, it's the magnitude of the moment and the magnitude of shear that we need to account for. Make sense? Cool. Okay. Any questions on lab 3 here? Great. So pretty straightforward. Let me know if you come up with any questions or have any problems. Shoot me an email. And yeah, have a good one. For sure.